Okay, my watch says 3 p.m. Is this consistent with everyone or early, late? Okay, let's start off. First, are there any questions about anything technically or logistically in CSE 373? On Piazza, you should be able to, we posted office hours for all the TAs and both the graduate and the undergraduate. There's two sets of undergraduate recitation sections, one on Monday, one on Friday. So there's a lot of opportunities to get help in here. I also have my office hours posted on Piazza, and so that's from 11 till 11ish till 12:30 on Tuesday and Thursday. So don't be afraid to come in there. Are there any questions about anything related to logistics of the course?
Yeah, I actually have a quick question about so in regards to like the big O problems. So the textbook mentions about like functions that like have like a dominance relation to others. So like when we have a big O problem on a test or on the homework, do we need to like actually like prove using limits that one function like dominates the other, or can we just simply say that, like for example, n cubed dominates n squared?
Okay, so we're going to go over what we mean by dominance today. You know, there's one thing about the big O notation. Again, once you get it in your head, certain things like, oh, well, the biggest polynomial is always the highest degree polynomial dominates all lower degree polynomials, or any exponential dominates every polynomial. All this stuff gets naturally in your head, and you can do this mechanically. That said, I do want to make sure people, what you call it, I want to make sure that people, try to understand where this is coming from. And so when we talk, for example, about for the daily problem, maybe I'll start to move on to the daily problem. For the daily problem, we define the big O in terms of these two constants, that basically a multiplier to ensure that a C multiplier C to ensure that it was bigger than the one side was bigger than the other side, and then n naught, a point at which beyond which we know that it's true. And once you understand how these work, some of these things you can kind of do in your head, know that these constants exist, and you don't have to think too deeply about it. But maybe it's a good idea to think about it. We'll talk about where some of this stuff comes from, and hopefully you'll understand where these things are. Some of you may be allergic to limits since you stopped taking calculus, okay, which is why I'm a little leery about it. But so bottom line, you should understand why these things work. And then I'm okay with you doing things in your head unless the assignment or the problem says differently. Does that answer your question?
Yeah.
Okay, not convincingly, but that's okay. If it still doesn't answer it by the end of class, you can ask me again. Any other questions about logistics? I got called, some people asking me about, some people were asking me about partners on the homeworks. I encourage people to work with partners. You don't have to work with a partner, but I think it's a good idea. So I encourage you to try to find a partner. If you really want a partner and you can't find one, a brave person would post to Piazza and say, hey, is anyone looking for a partner? A less brave person could say, mail Professor Skeena, and I will assign you with the next person who mails Professor Skeena. But the better you can figure it out, the better. Any questions? Okay, let's talk about the daily problem. And the daily problem, we talked last class about the big O notation. And what I'm trying to do is to figure out the relationship between these functions f and g. And we want to basically know whether the relationship is a big O order of meaning that g of n is an upper bound of f of n. We want to know whether it's an omega, where g of n is a lower bound of f of n. Or we want to know if it's a theta, meaning that they are tight. Okay? So let me think how I would do these kinds of things. So if we think about it, what is the first question asking me? The first question is asking me if f of n, which is n squared plus 3n plus 4, how does that relate to 6n plus 7? Now, the first rule that I would like to say, we'll talk about dominance a little later today, but basically the higher degree polynomial dominates things, okay? N squared is going to grow faster than n. N is going to grow faster than a constant, which like 4. And that would mean that the first term is greater than or equal to the second term, which is greater than or equal to the third term. The sum of 3 such terms is going to be at most 3 times this. Bottom line is, we can think about the relationship of things. If we just think about the big first terms, how is it, trouble. How is it that n squared, how does that relate to 6 times n? Okay, well, the 6 times n is just a constant. So I know that for whatever, I want to know basically, is there a constant times 6n, and I might as well just make it n, such that this c times n is bigger than n squared? Is there such a constant c? I claim the answer is no, okay? N squared is going to be n times n. The equation really, if you cancel by n, it's saying is n less than some constant c. If c is a constant like a million, okay, and n is something that it keeps growing, well, eventually n is going to be bigger than c. So this can't possibly be the relationship. What is the relationship between n squared and n? Well, if it was the omega, the sign would be different. Can we argue that that beyond some n naught, there exists a c such that c times n is going to be less than n squared?
Yes.
Well, if we cancel the n's, again, we've got, is there some point at which beyond which n is always greater than c? For all n naught, okay, greater than c, this is going to hold, okay? And so this is an argument that the omega relationship, the theta relationship holds. The big O does not hold. The omega relationship does. Theta requires both of them to hold. This, I argue, is an omega relation. Any questions about that? Okay, good. Let's try the second part of this, and this time I'll do it in blue, just so I don't have to erase anything. We're asking, how does n log a, n square root n, compare to n squared? That's really what the heart of the second part is. And they may look like different beasts. What is n square root n? Is there another way to write n square root n? What is that?
N to the power 3 by 2.
Right, so this is really something like we want to now know, how is it that, maybe I'll do it down here. How is it that n to the 3/2, how does that compare to n squared? Okay, that's really what I'm kind of trying to ask. And the way that I think about this is n squared could be rewritten as n to the 3/2 times n to the 1/2. Does everybody agree? You know, when you the way that when you have two terms, polynomials, the product of them, you add up the exponents. So n squared is n to the 3/2 times n to the 1/2. How does that compare to n to the 3/2? Well, is there any constant times this that's going to make this side bigger? Certainly, since we can cancel at n to the 3/2 on both sides, we could cancel it. And the real expression is now the comparison between 1 and a constant times n to the square 1/2. N to the 1/2 is the square root of n. As n gets bigger and bigger and bigger, the square root of n gets bigger and bigger and bigger. More slowly than n, but it gets bigger. Okay? So it should be clear that if I set c equal to 1, this is going to be true. Okay? And certainly the big O holds, because there is a constant 1 times the square root of n that is bigger than 1. Okay? Can I reverse the sign of this, less than? Is there any constant such that c times square root n is going to be less than 1? Well, if c was 0, but c can't be 0 when you're doing this. C has to be greater than 0. There is no value greater than 0, such that c times the square root of n is going to always be bigger than a constant times 1. So it is not an omega, only the big O holds there. Any questions about that?
I had a question.
Yes.
For this problem, is it possible that you can say that from a certain n not value and on, the square root of n is always less than n, so therefore you can sort of bound it at 2n? Like you can represent that as less than 2n, and then...
You're saying the square root, okay, so that's an interesting question. You're saying that there exists a point below which the square root of n is asymptotically, wait, you said the square root of n is less than what?
n.
The square root of n is less than n, that's certainly true, okay? So, I'm missing the meat for the punchline. Oh, you mean could I have done this before I factored it like this?
No, basically, like what I'm saying is that instead of saying that square root of n is n to the half and then multiplying that by n to get n to the 3/2, you could instead represent that as, instead of a polynomial, you could represent it as, I mean, it would still be a polynomial, but it would just be to the power of 1. So instead of n to the 3/2, it would be less than 2 times n, because so the square root of n is less than 1 times n. So
You're
if you
saying that
multiply,
okay, so you're saying that the square root of n is less than n.
therefore n
Once you
times
get
the square root of
big
n
enough
is,
n.
yeah.
That's certainly true. Okay. And if you needed to use this fact to kind of show that, that would be a fair thing to use.
Okay.
Of course, to be precise, you might want to prove this. How would you prove that the square root of n is less than n? Well, part of it is to say I'm willing to give you this because obviously n square root of n squared is going to be n. Okay, but anyway, arguments like that might very well work. I like this idea for understanding it, though, of pulling the pieces out and seeing what's exactly left.
Okay.
That's my idea, but there's different ways you could do it.
Got
Okay.
it.
Part of it is just to recognize that of what we're trying to do here. Any questions? Okay, the third one, maybe I'll even go change color again to show that I mean business here, is interesting because I want to compare 2 to the n with n to the 4th. Now, this is a seemingly more difficult thing or a weirder thing. 2 to the n is an exponential. N to the 4th is a polynomial of degree 4. Okay? Now, you probably know, it's probably fair to say on one level that you know that exponentials are always greater than polynomials. That's certainly one thing you should stick in your head. For large enough values of n, any exponential is going to grow faster than any polynomial or every polynomial. But how would we compare? Let's try to come up with a principled way. What would be an argument on how 2 to the n compares to n to the 4th? Okay, that's really what the heart of this thing is. And the way that I would think about this best is let's use a property that I'm going to show you guys later a little bit later in the lecture. What is 2 to the log n? Does anybody know what 2 to the log n is? 2 to the log, let's say the log base 2 of n, if you want to be precise. 2 to the log n is n. Okay, that's the definition of a logarithm, and I will show you that later in the class. But if you believe that, let me say that I could represent 2 to the n. I could pull out a 2 to the log n. I could pull out 4 of them. I'm going to claim that 2 to the n is going to be the same as 2 to the n minus 4 log n times 2 to the log n to the 4th. Does everybody see that this is an equality? If 2 to the log n is equal to n, okay, if 2 raised to the log n is n, 2 raised to the log n to the 4th is n squared, right? And 2 to the n is going to be 2 to the n minus 4 log n times 2 to the 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 log n. Does everybody see how I rewrote this expression and came up with an alternate expression for 2 to the n? A question here is an acceptable thing. Any question?
Yeah, could you explain where the n minus 4 log n came from?
Yeah.
Well, what is it? If you think about it, if I want to have a bunch of terms multiplied to 2 to the n, 2 to the n is 2 times 2 times 2 dot 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 to the n, right? Now 2 to the log n is log n 2's. 2 to the log n times 2 to the log n is going to be 2 times log n 2's. Okay? So really, this is kind of like a balance here. I mean, the key, I guess the key identity here is 2 to the a plus b is equal to 2 to the a times 2 to the b. Does everybody remember this kind of thing? This shouldn't look funny to people, right?
Yeah.
And if that's so, that's exactly what I'm doing. I am pulling out, I'm taking my set of n2's. This is maybe the picture that I would draw. Here are n2's. I'm pulling out one group of log n, another group of log n, another group of log n, and another group of log n. And I'm going to have some left over. In fact, I'm going to have n minus 4 times log n left over. What is the purpose of that kind of an argument? Okay, that kind of argument then says, if 2 to the log n is the equivalent of n, this says that 2 to the n is going to be n raised to the 4th times 2 to this number of 2's. Okay, and that number of 2's is going to be positive, a big number. So how does 2 to the n compare to n to the 4th? This has got to be much bigger because we can cancel this and cancel this. And what we have left is this that's going to keep getting bigger as n gets bigger. So this is an argument that this side has to be bigger than that side. And we are back in the relationship of this being an omega. Any questions about that? Okay. Again, the important thing to file away is that exponents are always bigger than polynomials. And it's kind of an argument like this that is going ahead to do it. Any questions?
For these types of questions with like exponents, like, are you allowed to just demonstrate it by just picking a C and N value and showing it for that, or would you have to like
What was
for
the word before value? Are you allowed to demonstrate it by showing, oh, C and N values?
yes.
Yes, the way that you would argue about whether something holds in a big O sense, an omega sense, or a theta sense is to show me the N naughts, show me the C's, where it's always winning. Okay?
Got it.
And that's basically what I was just doing. I was showing you, we were doing this thing to see that this is always going to win ahead of the other one. Okay, any questions? Any questions about the problem of the day? If that's true, any more questions? Bing. Okay, fair enough. Okay, so I want to talk a little bit more about the big O and dominance and logarithms today. Those are my topics for today. And one thing that, just to make sure we understand how the big O works, is something related to multiplication. Okay, and understanding what happens with multiplication. What should be clear is if I want to know what the analysis of a function, f of n, okay, which may be f of n, let's say f of n was n cubed, okay, and I want to know what big O of n cubed is, it should be clear that multiplying n cubed by 100 and asking what is 100 n cubed, okay, multiplying it by a constant like 100 doesn't change its status given the big O notation. Why is that? It should be clear. Is there a constant? Let's think about it. We have 100 n cubed here. On the other side, we say n cubed. If we want to prove that it's order n cubed. Is there a constant times n cubed such that the right side is bigger than the left side? What would be a constant for that? What would be a value of C for that? Should be 101 will do it, right? And what about the other way? Is there a constant times n cubed such that we can make C n cubed less than 100 n cubed? Okay, what would be a constant for that? I'm hearing 99. Okay, multiplying a function times a constant does not change its status by any of these big O notation things. Okay, if you think about it, in the big O notation before, you had an old constant, C, to argue that left side equals right side. You multiply one side by a constant, another constant. The product of those constants on the right will keep the balance that it had before. Notice that this is not true. We can't ignore multiplication when we multiply functions together. What do we know if we have a function f of n that has the property that it is order n? Let's say we know that this is order f of n. And we know f of n is order n, and g of n is order n squared. What is the product of something that is order n times order n squared? We know that the first function is less than or equal to some constant c1 times n. We know that this other constant is less than or equal to some constant times c2 times n. What do we know about the product of them? The product of f and g is going to be less than or equal to c1 times c2 times n cubed, right? Because if this is less than this and this is less than this, the product of them is less than c1 times C2 n cubed. The n cubed came from n squared. So what does that mean? We now have a constant such that this is less than or equal to the constant formed by the product of these two times n cubed. That means that the product of these two functions is big O of n cubed. And a similar kind of analysis holds for the omega. If the first one is greater than or equal to some constant C1 times n, and the other one is greater than or equal to C2 times n squared, the total product is going to be greater than or equal to C1, C2, n cubed. That constant is now the new constant that we use here. Okay. Bottom line, when you have functions that are not constants, you have to multiply them out in the big O. Any questions about it? This is why when we're analyzing algorithms with nested loops, 4i goes from 1 to n, and 4j goes from 1 to n. This inner loop, okay, what is going on here? Let's say we're going to type x equals x plus 1. Let's say that's your algorithm. This statement took constant time, that's theta of 1. N times theta 1, this whole nested thing is going to be theta of n in the worst case. And if that's nested within another loop, it's going to be n times this. The whole algorithm was theta of n squared. Does everybody see that this is kind of why we get nested loops multiplying, okay, when it comes to the big O? Any questions about that? Any questions of any of this? Okay, good.
I have a question about the theta.
Yes.
Like, in which cases, like, theta is gonna be equal? Sorry, I think you explained it, but I just
Well,
didn't.
theta, when we have a theta relationship, we have something where the upper bound equals the lower bound, right? Or when there's an upper bound that is a constant times something and a lower bound where the constant is something. We prove separate upper and lower bounds with different constants, okay? And we show that that actually holds.
Oh,
So
okay.
in this case, we're talking about the worst case running time. The worst case running time, if we have something that just is adding two integers, clearly to add two integers takes one step that is upper bounded by a constant, 1 or 2, and lower bounded by a constant, 0 or 1, okay?
Mm-hmm.
So we know that a single operation, the number of steps it takes is going to be theta of 1, right?
Mm-hmm.
If we have something that is going to be upper and bounded by a constant, and we're multiplying it by n, well, this thing is going to be upper and lower bounded by a constant times n. So
Okay,
that's how
yeah.
we got this theta. And how we got, when we did it again, we got the theta holding again. Any questions?
Gotcha. Thank you.
Good luck. Okay, let's look at how we analyze an algorithm using the big O. Again, I hope this is going to be the last lecture I talk about the big O notation purely as a math notation. Okay, the big O notation is not an exciting thing. It's just a language for talking about complexities. Let's look at, you know, how we can talk about the worst case running time of algorithms. Okay, because that's really what we're in here for. That's really the business. And so how do we come up with a theta bound or a big O bound or a, you know, an omega bound for the running time of an algorithm? How do we reason about the efficiency of an algorithm? And what I will say is that usually, to a first approximation, if I give you a piece of code, you can read the running time complexity, the worst case complexity of an algorithm, usually off pretty straightforwardly once you're looking at the code. If it's all it's got are for loops, it's easy to kind of do. And when I try to analyze an algorithm, whenever you analyze an algorithm, you've got to realize that you're dealing with a written piece of code, a pseudocode for the algorithm or something like that, has got to be in your head, okay? At first, you know, when you've analyzed a lot of algorithms, you can kind of keep them in your head and you can reason about them that way. But maybe at first it's easiest to realize that whenever you have an algorithm you want to analyze, first write it down so you know what you're talking about. Whenever I tell you, oh, quicksort is n log n, what am I doing? In my head, I am seeing a piece of code that is a quicksort. And I am doing some reasoning about that, okay? So what I'd like to do is just get us a little practice looking at code and trying to reason about it. So what is the algorithm I want us to first reason about? Selection sort. What is selection sort? Selection sort is an algorithm that takes a, let me just try this, 3, 1, 4, 2, 5. Well, let's put it like that. And goes through, if we want to sort an array like that, what does selection sort do? It goes through all the elements, finds which one is the minimum element. Okay, in this case it's 1. And then do a swap so that the minimum element becomes first and the array is then unchanged. But there's kind of this distinction between the sorted part and the unsorted part. What does it then do? It goes through all the elements of the array, finds the next element that is smallest, does a swap. Okay, and now what did we end up with here? 4, 3, 5. It then goes through the array again, finds the minimum, does a swap. 1, 2, 3, 4, 5. Asks ourselves which one of these is the minimum, does a swap to keep it basically where it is, and gives up at the last element because and then does the same thing with the last element. Finds where the smallest one, puts it in there, it's going to be in the right spot. So this is an implementation of selection sort. What is it doing? For each of the n times through the loop, that was bad, it did something. For each of those n times through the loop, find the minimum element in the remaining chunk of the array. See, I minus 1 is, we have a loop that's going to say start from the 0th part, go to the first, second, third. This is going to say we're going to find the ith element by ith smallest element by looking at from the I plus first to the last element of the array and find the min. Okay? What is the running time of selection sort? The way that I would reason about it is the following. I would say a minimum setting the variable j to be the min, that's going to take 1 step. If this is less than that, that's just doing 1 step. It's doing a comparison. That's a constant amount of work. This whole if statement takes constant time. The loop is going around from I plus 1 to n. How many times is that loop going to go around? Well, the most it can go through in the worst case would be it would go around n times if you have n elements. That tells me that all the stuff within here is going to be n steps, setting min to be min equals I, that's going to be one step. And we have one external loop around everything. Yes, there's another one step down here. We have an external loop around it. It's going to look something like n times 1 plus n plus 1. This I claim is n squared. Okay? And I'm reasoning about this as an upper bound because I told you what's the maximum amount that this loop could go around. Okay? So this is an argument that the worst case running time of this is order n squared. Any questions? Is it actually n squared? Well, if we look at this algorithm carefully, there is no if that is going to change the number of times that the loop is going to go around. For me to argue that the worst case running time is not only upper bounded by n, but really is n, observe that it takes this amount on every single input. So in fact, I could make a stronger statement and say that selection sort is theta of n squared. Any questions? If I had told you that selection sort was order, the worst case running time was order n cubed, I would be making a true statement, a not very interesting statement. Okay? I'm giving you an analysis of the complexity where my analysis is too soft. O of something is an upper bound, right? If I want to tell you guys, sometimes people want to know how much money do you make as a professor. Suppose I tell you, I'm going to tell you the truth now. I make less than $1 billion a year. Okay? Did I say something true? Yes. Did I say something interesting? Probably not. Certainly not if you wanted to learn about what I make for an income, right? So an upper bound is the big O. A theta bound is when we really know a tight value on what this algorithm does. And I gave you an argument that it never took more than n squared time. And in fact, because I noticed that it always takes, in fact, exactly n squared time, this one is theta of n squared. Any questions how I did that analysis?
I have one question.
Yes, please.
For the inner loop, isn't it supposed to be running like n minus I plus n minus I minus 1?
So you're telling me that the
Or
inner loop is going around from I minus 1, I plus
no.
1 to n.
Yeah.
Now, when I was looking at an upper bound of it, I said that it was going to go around from 1 to n, because certainly I gets as small as 0, right?
Okay.
So that's why I have it as an upper bound. But you're right in saying this inner loop does not always go around n times. The outer loop always goes around n times. Many times does that inner loop go through? Actually, how much does it go through on average? If we think about it, how much does it go through on average?
N times, like average, I think it should be n times.
Average, if we want to be a little bit more precise, what do we know? The first time it goes through, the inner loop goes around n times.
Yeah.
The second time it goes around n minus 1 times. Third time n minus 2, ... eventually down to 1. What is the average of these values? Okay. I'm going to claim that the average of the first and last, n plus 1 divided by 2. In fact, each one of those pairs is at, this is going to have an average value of n over 2, right?
Yeah.
So if we're really careful about doing the analysis, the inner loop only goes around an average of n over 2 times, okay? Of course, something that goes around over n over 2 times is going over around theta of n times. Does everybody agree?
Yeah.
Because there's a constant n over 2 that's less than it, and a constant 1 that is n times n that is greater than it. Okay? Any questions? So what is my analysis? Again, my analysis was basically outer loop goes around n times, inner loop goes around at most n over times. Thus, the algorithm takes at most n times n, or O of n squared. If I really want to argue the theta n, what I would say is, you're right, the inner loop did not go around n times. One way to argue it is that the first n over 2 times through the outer loop, okay, the inner loop was going around, okay, at least n over 2 times, okay? So if we think about it, the first n over 2 iterations of selection sort are the expensive ones. Each one of them required scanning through at least n over 2 to get the min, okay? And therefore, the total time spent was at least n over 2 times n over 2, or n squared over 4 steps. And that's how I got my theta. Any questions about that? Any questions about how you might take selection sort and see that it is in fact a worst case n squared algorithm? Okay, good. And again,
Wait, so I actually have a question real quick.
yes.
So when you're saying it's a theta and n squared also, that means also the best case is n squared as well, right?
No, it does not. Theta n, remember, theta n is actually a tricky thing. Does that mean that the best case is n squared? Not necessarily. We could, let's say we had a variant of selection sort, that the first thing it did was check to see if it was completely sorted. If I have n items, and I want to tell whether they are already sorted, how much time would that take? I hear people telling me order n. Right, I have to compare. Is the first element less than the second element? Is the second element less than the third, fourth, fifth? Does everybody believe I could write a version of selection sort that says, if it's sorted, stop. If not, do the selection sort. The best case of selection sort would then be if the element array was all sorted, right? Then the algorithm would run in what? Does that order n time? Does everybody kind of see that? But there still exists inputs where that version of selection sort will take n squared time. So remember, we're interested in the worst case running time of the algorithm. The worst case, if I'm saying that an algorithm is theta of n squared, that means that there is an upper bound saying it always runs in n squared time. And you can actually point out an example where it really takes n squared time. That there's no way that further analysis is going to lower that bound. Okay? Does that make sense now? Let's not ask again. This maybe is a.
I'm still a little kind of confused.
But remember, what are we dealing with? We want an algorithm. We want to find some function f of n, where f of n is the worst case running time. If we are talking about the worst case running time, we want to say, what do we know about the worst case running time? Okay? If I give you an analysis that the worst case running time is always less than g of n, if I say f of n is O of n squared, I have proven that the worst case running time of this algorithm is no worse than n squared. But if I tell you that it's theta of n squared, it means the worst case running time of this algorithm is n squared. Okay? And that means I can show you an example where this algorithm, your algorithm is as bad as n squared. If O of n is an n squared is the upper bound, The lower bound could conceivably be order n or even log n or who knows what. Okay? But when I tell you, give you an example, I can show you that it takes that much time on that. That's when I get to say the worst case running time is theta. Because I proved an upper bound of this, and I have shown you that there's an example that actually takes that time. Any questions about that?
I had a really quick question about that. Is there a difference between saying that an algorithm runs in theta n squared worst case time and just theta n squared time?
Well, when you say theta n squared time, you're kind of not really saying what it is. Is
Okay.
that dancing time, or I don't know what that means, okay? Really, you should be precise. We usually assume it means worst case time.
Okay.
If you want it to mean something different, then you darn well better tell me what it is, right?
Got it.
Okay. Any questions? Okay, that's selection sort. Let's do it again with insertion sort. Okay, what is insertion sort? Insertion sort is an algorithm that, again, is going to go around n times. Let's take a look at our numbers again. I don't remember what my numbers were. 3, 1, 4. Let's make it 2, 5 this time. I think that's actually what I think I had before. Anyway, what is it going to do? It's, instead of finding the min, it's going to start with the first element and say, just considering it by itself, so far, everything to the left of this is a sorted array. The next element we're going to want to slide into position. We have to say, are you smaller than the previous guy? If so, swap. And keep going until it hits the right spot. So now, we've got after that, in the second iteration, 1, 3, 4, 2, 5. If we have a 4, it'll take only one comparison to decide 4 is bigger than 3 and not feel a need to move in. So in fact, at that point, we can stop looking. For a 2, once that's been put, once we now are faced 1, 3, 4, the 2 we have to compare with the 4, we have to compare with the 3, and then we have to compare with the 1 to decide where it actually ends up, okay? So this inner loop is now a while loop. And this thing might go around only once. What would be the best case for this insertion sort? What would be a permutation where this inner while loop didn't do very, was always being answered quick?
No swaps at all.
No swaps. What would be the input that would give me no swaps if I give you n items? They're already sorted, right? If I ask you 1, 2, 3, 4, 5, I'm in the right position. Nope, I'm not going to change. I'm happy where I am. I'm happy where I am. I'm happy where I am. The best case of this is order n, right? What is the worst case of this thing? Okay. Well, one observation is, so there are a couple ways of analyzing this. Before I even look at the worst case, I want to look at this code and say, what's the worst thing that can plausibly happen? The outer loop is going to go around n times. What's the worst this inner loop could go by? What if the last element that I'm inserting was in fact first in sorted order? I have to compare it against all the n-1 other items. This while loop is going to go around less than or equal to n-1 time. So what do I know? I know it can't go through more than n times because it's only comparing against other elements in the array. N times at most n-1 is O of n squared. And that reasoning is enough to say that this is an n squared worst case time. The inner loop can't possibly go through more than n times. But if I want to prove a theta, I want to prove that this algorithm actually can take n squared time. And what is the input where this thing actually takes n squared time? Well, what if I give you a reverse sorted input? Then this is going to do one comparison. This is going to have to do two comparisons. This is going to have to do three comparisons. This is going to have to do four comparisons. Does anyone remember what is the sum as I equals 1 to n of I? That's the sum of 1 plus 2 plus 3 plus 4. I think I just did that one, right? What does that work out to? That is something like n times n plus 1 over 2. Okay? And that means that if I give you a reverse thing, this is going to take something like a half times n squared comparisons. If I know on that example it's going to take a half n squared comparisons, that means that it's going to be omega of n squared. If I know that the worst case running time is O of n squared and it is also omega of n squared, therefore it's got to be theta of n squared. Any questions about that? Do people see starting to see how I analyze these algorithms, given the thing on, printed on paper? This is an important skill. You should be able to take a look at a piece of code and be able to come up with an upper bound of it pretty simply in most cases. Any questions? Whether that's the really tight bound will turn out to be sometimes harder to show, okay? But getting an upper bound with the big O is designed to be easy. Any questions? We'd like that to be as tight as possible, but at least getting something is usually pretty easy. Any questions? No, okay, good. Any other questions about how we analyze code?
I have one question
Yes.
about the inner loop being like about the whole thing as a omega is n square, right? So can you explain that one more time, like omega being
Omega is saying
is
that the running time is at least some constant times n squared, right?
yeah.
If it's at least some constant, I have to prove to you, is it at least some constant times n squared? And I'll say, sure. Look at this reverse sorted thing. It is going to take at least a half times n squared, right?
Yes.
That says if the worst case running time is at least a half times n squared, that means that it is omega of n squared, right?
Okay.
And when I tell you it's n times at most n, that's going to be the argument that's at most n squared. If something is at most n squared and at least n squared, well, then it is n squared.
Okay, yeah, gotcha.
And that's the reasoning that we want. Okay, any questions about that? Okay, this gets us into the concept of asymptotic dominance. And again, I want to make a quick analogy, maybe it's a dumb analogy, is the reason we care about the big O notation is it lets us kind of identify when one function is strictly bigger than another in a way that means something. Okay, and the example that I guess I would give, there are two kinds of spaceships that have been proposed to sort of sail to other planets and galaxies. One of them I'm going to call is a badass rocket, which is this big thing that, goes, burns a lot of fuel, shoots into space at, gets going 20,000 miles an hour and just keeps going. In space, you never hit any kind of once you're there, because space is a vacuum, you never slow down. So the typical rocket that we have is something that The speed is basically what its maximum speed is after it uses all its fuel, and then it doesn't change. Now there's this new proposal for a spaceship, which is like almost like a kite that has a sail, okay? And there's this tiny stream of particles that comes from the sun that has a very gentle breeze. And that gentle breeze, if you have this sail, is always going to, there's always going to be a force on that sail. And that force is going to push the spaceship faster and faster and faster. It's going to start out doing nothing. The force of this solar wind is very, very, very light. I've heard it's like the gravitational force on a sheet of paper. But if you have one force, that's going to give acceleration. It's going to keep getting faster and faster and faster. Start very slow. But if something starts slow and keeps getting faster, it will eventually be faster than something that is moving at a high speed. And that is kind of the idea that we want with asymptotic dominance. We don't care about small n. We care about what's happening in the limiting case. Okay? So let me again talk about the kind of major algorithm complexities we are going to see in this course. There is the function log n, which I certainly hope to go into more detail very soon about. There's the function n, which is the linear time algorithm. What's an example of a log n algorithm? Does anybody know of a log n algorithm?
Binary search.
Binary search. Okay, we'll talk about that. There's n log n algorithms. What's an n log n algorithm? Something like merge sort or something like that. What's an n squared algorithm? Well, something like bubble sort. What is an example of a 2 to the n algorithm? Something that goes through all the subsets of things. So I guess if you had tried to solve the movie star problem by brute force, scheduling problem by brute force, that would have been a 2 to the n problem algorithm. And n factorial is what the traveling salesman or that robot tour problem would be. Suppose, let's say, we're able to have a computer that can do, 1 million instructions a second or something like that. How much time does it take an algorithm with these complexities to work on an instance of size n? The important thing, if you look at it, as n gets bigger, you see really dramatic separations between these algorithms. The logarithmic time algorithm doesn't break a sweat even for a billion. You can live maybe with a linear time algorithm in a billion. Maybe if you're willing to be patient, an n log n algorithm takes half a minute. That's not so bad. But an n squared algorithm, a quadratic algorithm, you're already talking about years. And when we talk about exponential time algorithms, forget about it. Okay? A 2 to the n algorithm, by the time you ask it to do something of size 100 elements, you're already talking about umpteen years. And for permutations, by the time you talk about 30, you're talking about umpteen years. Does everybody see that these complexities functions make a big difference when n gets big? Okay? And what's interesting is we can kind of break all algorithms into a relatively small number of these complexity classes, where their analysis of running time is typically, in this class, going to be one of these. Not always, but typically. Okay? So what do we learn? An exponential algorithm is doomed to fail for any reasonable n. A quadratic algorithm is going to be hopeless by about 1 million. And maybe you can get up to 1 billion with n log n, but it's starting to be visible. A log n algorithm never sweats. Any questions about these? How do we prove whether one class is different than another? there's this way of testing dominance, which we define in terms of limits. Okay? We say a function f of n dominates in function g of n if the limit of g of n over f of n goes to 0. What does it mean as n approaches infinity if this goes to 0? Okay? It means that g of n is much, 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 much smaller than f of n. Okay? And when we say that g of n is much, much, much smaller than f of n, we actually introduce another notation, the little o notation, meaning that it grows strictly slower than, okay, this thing. So what are examples of functions where this limit is true? What is the limit of n over n squared? Well, that's the limit of, if we cancel it, 1 over n. As n gets bigger and bigger and bigger, what does 1 over n approach? It approaches 0, right? So that's an argument that n squared dominates n. Okay? Any questions about it? So implicit within this notion of the big O, this dominance, is that whenever you have two polynomials, n to the b and n to the a, if b is less than a, the limit of n to the b over n to the a is going to be n to the b minus a. And that is going to go to 0. It's 1 over something. If a is bigger than b, the limit of this is going to go to 0. So we say that n to the 1.99999 is dominated by n to the 2. Does everybody kind of see that? In practice, you may say for reasonable sized n, n to the 1.999 doesn't look too much different than n squared. But as n gets to be infinity, the ratio of this to this is going to be something like 1 over n to the 0.00001. 1 is going to stay at 1. N to the 0.00001 is going to eventually get to infinity. The limit is 0. So we can determine the relationship of dominance between any pair of polynomials. We can say when we add a lower order term, it doesn't dominate it. What is the limit of n squared over n squared plus n? Does that go to infinity? Okay, does that go down to 0? I claim it's going to get very close to 1 as n gets bigger. Okay? Certainly it doesn't go to 0 because we know that n squared plus n is going to be less than 2n squared. Therefore, n squared over 2n squared has got to be less than 1/2. Okay? And in fact, so bottom line is that there isn't a dominance when we have an additive term. Any questions?
Yeah, how do you add a little o of n, I believe it was, or in the previous slide? Yeah, sorry, n to the a.
So what was this saying? This was saying, what is the ratio of n over a? Let's think a is going to be 3, n cubed, something that grows strictly slower than n cubed. N squared grows slower than n cubed, right?
Yeah.
What is the ratio of n cubed over n squared, n cubed plus n?
Eventually
As n gets
1.
larger and larger and larger, this gets closer and closer to 1, not 0.
Got it.
Any questions about that? So what you need to understand is that these are the most common complexities. I think almost all the algorithms we're going to talk about in this class. are going to have complexities of these prop fives. This is the dominance relationship between them. We always want our algorithm to be as far to the right as possible, because that's going to mean, if the worst case running time, to be as far to the right as possible, because that's the, those are the ones that are faster. Any questions? Now, when you take a sufficiently fancy algorithm course, you will learn about algorithm complexities for many other functions. There do exist fancy algorithms with different complexities. And this kind of gives you an idea. Let's look what's interesting. Does anybody know of an algorithm that runs in n cubed time? Actually, multiplying two n by n matrices runs in n cubed time. Okay, so that's an interesting example of this thing. But bottom line is, there are these more complicated complexities that you have to worry about. You should know that n to the 1 is certainly going to grow much faster than n to the 1/2. So we've got a dominance relationship here. It should be obvious that log n squared, which is log n times log n, that's going to be bigger than log n. Okay, because if you cancel this, the limit is log n still goes to infinity. Anyway, bottom line, recognize that in more sophisticated analysis, a lot of esoteric functions come up, but we're hopefully going to avoid that most of the semester. Any questions? Alpha n, there's a question about alpha n. This is the inverse Ackermann function. This is a function that is famous for being incredibly ungodly slow growing, but eventually gets to infinity. And turns out it comes up in some algorithm analysis. Okay? But again, I don't think we're going to talk about it in here. Any questions? Oh, good. What I'd like to talk about for the rest of the class is logarithms. And logarithms is a very, 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 very important subject in here. You got to know where a log comes from. Okay? And what is a logarithm? Well, the definition of a logarithm is simply the inverse exponential function. When you say that y equals b to the h, b to the x, what you're really saying is that x is equal to the log base b of y. A logarithm is basically, what is the exponent I need to raise something to get to a target. Okay, so earlier I said that 2 to the log base 2 of n is equal to n, right? Why is that? What is the amount that I have to raise 2 to get to n? Well, basically, by just doing this kind of thing here, y is going to be n. Okay? Does everybody see that this expression can be written where b is equal to 2, x is equal to log base 2 of n, and y is equal to n. Okay? And that's exactly what we get on the right side. Logarithms are important because they measure how many times we can double something. What is this logarithm statement meaning? It says we could start at 2 and keep doubling, doubling, doubling a total of log n times until we get to n. Logarithms are going to count how many times can we start at 1 and double till we get to n, or start at n and keep halving until we get to 1. That is why they are important in algorithm analysis. Any question what a logarithm is? This is the one thing you have to understand. in the course of doing algorithm analysis, we're going to come up with logs, and they're going to pop out of our analysis. And people are going to say, well, where did that? It came because we are repeatedly having something or repeatedly dividing something to get between 1 and n. Any questions? So let's look at some cases where in algorithm design and computer science and things like that, logarithms come into play. We said earlier about binary search. What was binary search? You want to try to find an element n in a sorted array. You compare your key to the middle element. If the key that you're looking for is greater than the middle element, it lies on this side. And you can throw away the half on the other side. In one step, I have halved the number of elements that I had. Originally, I had n elements. One comparison later, I've halved it. Another comparison, I've got it down to n over 4, n over 8, n over 16, ... How many times can I have it before I get to 1? That, by definition, is the log base n. That is why binary search is a log n algorithm. Any questions about that? Okay, that you got to feel that in your bones. This one's important. Suppose we have a binary tree. Suppose I want a binary tree that has a total of n leaves in it. What is the height of a binary tree that has a total of n leaves? Again, in these binary trees, I've got a root. The leaves are the things on the bottom. If I have a binary tree, meaning that at each point it's split into 2 subtrees, what do I get? Every time I go from one layer to another, my number of nodes went from 1 to 2 to 4 to 8. It's clear that every time I go one level deeper in a tree, I double the number of nodes. Does everybody kind of see that? I started at 1, I got 2. I started at 2, I got 4. How many levels will it be till I have n nodes there? It's how many times I double from 1 and get to n. After a height of log n, my tree will have n leaves. Any questions about that? That's why a lot of algorithms on trees, okay, are going to be log n in height when we talk about data structures. Any questions? Suppose I want to build a new computer and I want to represent any number from 0 to 2 to the I plus minus 1 in my word length of my computer. How many bits do I need to represent a number as big as 2 to the I plus 1? Well, what happens when you add 1 bit? What's the biggest number in binary you can represent in 2 bits? Guys out there, what's the biggest number you can represent in binary in 2 bits? Does everybody agree it's 3? What's the biggest number I can represent when I add 1 more bit? That goes from 3 to 7, okay? Actually, I guess another way to think about it is, or maybe it's a little easier to see it, is that there are a total of 4 numbers I can represent with 2 bits. When I add another bit, I double the number of numbers I can represent. Does everybody see that? If I want to represent 2 to the n different numbers, how many bits do I need? Well, 1 bit gave me 2 numbers. How many bits do I need? Something like log n. Because I need to double it log n times. Okay? Okay, so if I want to get up to 2n, I've got to do the log of 2 to the I. The log of 2 to the I is I. Does everybody agree that I would need I bits, okay, to get up to 2 to the n, to get up to 2 to the I? Which is equivalent to saying if I want to get up to n, I want to get up to log n. I want to have log n bits. Any question? Log n counts the number of doubles or halves that we have. Any questions? Good. What other things about logarithms are kind of interesting or important? Well, one thing you used logarithms for in a math at one point was to use it to kind of multiply things. There is this relation you've probably seen, which was that the log base a of x times y is the log base a of x plus the log base a of y. Okay? This was very, very useful to, what you call it, to, okay, this was very, very useful to multiply numbers before people had calculators. I don't know if you've ever seen a slide rule or you ever saw an old man with a table of logarithms. This was a way to convert between multiplying things and adding things, and it was easier to add things. Okay? But it becomes very interesting to work with this relationship. What is the log, let's do it. What is the log base a of a times y? Okay? The log base a of this is going to be, what is the exponent that if I erase a to the h, I am going to get a times y. What is that going to be? What is the value of h? What's that exponent? Such that a to the h is going to be a times y? I claim that's going to be equal to 1 plus the log base a of y. And that's exactly what this relationship is. Any questions about that? Okay? It's important to understand where logs come from. Okay? Any questions? Let me give you one, I think, final important property of logs. Okay? Which is that the base of the log doesn't really matter very much. Okay? So, again, what is the definition of a logarithm? We said that by our definition, I'm now in trouble. Boom. C to the log base c of x is equal to x. This is the definition that implies what a logarithm is. Okay? One thing that's true or interesting is that there is a relationship between logarithms and their bases, okay, which goes as follows. The log base b of a is equal to the log base c of a divided by the log base c of b. Okay? In high school, you saw this. You may not remember it, but in high school, you saw it. But I want to think about what this means. Suppose we rewrite a and call it n, because we know that n is a variable. And maybe this now becomes clearer. What does it mean if we have an expression that says that the log base b of n is the same as the log base c of n divided by the log base c of b? Suppose b was something like 2. Okay, hopefully I can do that. And c was something like 100. How does the log base 2 of n compare to the log base 100 of n? Well, we're dividing it by the log base 2 of 100. What is the log base 2 of 100? It should be seen as a constant, okay? Log base 2 of n is a number you get from your calculator, okay? if log base 2 of n is equal to log base 100 of n divided by a constant, what does that mean with respect to our theta notation? Okay, it means that basically log base 2 of n is equal to theta of log base 100 of n. Okay, and therefore from a big O perspective, a base 2 logarithm is no different than a base 100 logarithm. Any questions about that? So an interesting thing when working with logarithms is that the base somehow doesn't matter very much.
How did you get the theta notation?
Well, what do I say? The theta notation means what? That there's a constant. What do I know? Suppose I know that log, based on this expression, log base 2 of n is equal to log base 100 of n divided by the log of 2 of 100. What is the log of 2 times 100? Log base 2 of 100. I think that's something like about somewhere between 6 and 7. But whatever it is, this is a constant. Does everybody agree that this is a constant? This is really saying that log of base 2 of n is equal to some constant times log base 100 of n. If this is equal to a constant times that, there is a constant c such that this becomes an upper bound. And there is a constant a little bit less than c such that it's a lower bound, right? That's where the theta comes from. If this is an equality relationship and this is a constant, then this is both an upper bound and a lower bound. This says that log base 2 of n is the same thing as log, base 100 of n in the big O sense. Any questions about that? I know we're running a little long, and I know we are making people nervous. Any questions about that? That said, I just want to tell you something funny about logarithms, so you can think about it. If you go to look around the world, you can sometimes see logarithms in logarithmic growth in many things. Again, I think that what's good about an algorithm thing is that you can sometimes see these concepts in things that emerge not necessarily in computer science. I had a friend who was a lawyer who was studying for the bar exam, and he had the federal sentencing guidelines, the law that, the kind of rules that govern how much time you should get for stealing some money. And I saw a table like this in the federal sentencing guidelines, which said that if you stole this much money, how many points of criminal sentence should you get? Points may be mapped to years or months or something like that. What do you see when you look at this table? Can anybody see anything interesting when they look at this table? What is happening to the numerical quantities here as we go from one row to the next?
The money is doubling.
It looks basically like with every level, the amount of money you have to steal to get the next unit of punishment doubles. Does everybody kind of see that? That every time you steal twice as much money, you only get 1 unit of punishment. What does that mean? That's an important lesson if you're in the right line of work. It says that your sentence is going to grow logarithmically or very slowly with the amount of money you steal. So what's the lesson here? If you're going to go into a life of crime, It pays to steal really large amounts of money rather than small amounts of money, because the sentence grows much slower than what your gain is. Any questions about that? Okay. Hopefully you guys will stick to computer science and not crime. But if you have trouble with this class, at least take this lesson away if you decide to change your career. Any questions about that? If not, thanks for your attention. Look at the logarithms. Make sure you understand the logarithms. And we will talk about things on Thursday. Thanks for your attention.